Good morning, everyone. This is day one of our 1.03 lesson. I believe we only have two parts to this. Let me just double check. We do only have two parts. So we have today, Monday, and then we are reviewing on Tuesday for the exam. I know you're all very excited. So really, this unit was only two sections, 1.02 and 1.03, but of course, those sections had more than one part to it. But let's get started. Bell work. So factorials, we want to rewrite these factorials as a three-factor factorial. For example, 6 factorial can be 6 times 5 times 4 factorial. I could also make it 6 times 5 times 4 times 3 factorial. All right, any volunteers want to do any of these? I know some are much harder than the others, and that's okay. Volunteer. All right, Danica, do number 1 for me. Let's see. Antonio, you can do number 4. Anybody, any others want to take a shot at it? Remember, guys, it's okay to be wrong. I think it's really good to be wrong during lecture, because then once you learn from mistakes, and so that's why we're here in class, right? To learn from our mistakes. That way, we take the quizzes and the exams, we don't make mistakes. I don't have tools. Oh, I have to turn that on. Hang on 1 second. Okay, you should. Hold on, sorry.
Yes, Katie, I seen you raise your hand.
All right, anybody else want to do any of these?
Katie does. I don't know which one though.
See which one? Number 5, go for it. All right, number 1, that would be a correct answer, 10 times 9 times 8 factorial. So having something factorial, some number or variable factorial, means you're multiplying that number times every number descending down to 1. That's all factorials are. All right, so it looks like Katie trusted Antonio to be correct. He is not. Actually, you guys have very different answers. So 4 and 5 are actually incorrect. So you have to think back. We'll do 4 and 5 first. So I'm going to go ahead and delete what you both have there. So you need to, I think the good idea for everyone to review their exponent rules. And out. Right. So number 4. Number 4. So back to your exponent rules. Let's pretend n is 10. So if n is 10, that means we have this n. If n is 10, that means I have 2 to the 12th. Oh my goodness. It's not right for me at all. Drive me nuts. All right. Hold on, maybe my finger works better. Yeah, it does. I'll use my finger. So we have let's say n is 10, so I have 2 to the 12th power. Exponent rules. They must have the same bases and you add. So if I want to factor it, I have to subtract the exponent. So I could rewrite this as 2 to the 11th times 2 to the first, right? Because 11 plus 1 is 2. So looking at 2 to the n plus 2, 2 to the n plus 2, we want to rewrite this as two factors. So I'm going to subtract 1 out of the exponent. So it's really simple. What's n plus 2 minus 1? People in chat. Yeah, n plus 2 minus 1 is n plus 1. So I can rewrite this as 2 to the n plus 1 times 2 to the first. Antonio, I don't know what you wrote. I forgot, actually. I think you wrote 2 to the n. Yeah, I don't know what you wrote.
It was 2 to the power of n times 2 to the power of 2.
Okay. Actually, that would work too. Yeah, sorry.
You're good. It was Katie who put the plus.
Yeah, you know what,
Yeah,
Antonio, I
that's
was
good.
looking for you to just subtract 1 out. But yeah, Antonio's answer was also correct. You could write 2 to the n times 2 squared. And what he did was he just subtracted 2 out of the exponent instead of 1 like I did. And the problems that we're going to do later on in this lesson, you may have to subtract 1 or subtract 2 or subtract 3 out of the exponent. So that means that for this next one, I can write it as 2 factors. I can just subtract 1 out of the current exponent. So I can rewrite this as 2 to the 2n. I'm so irritated by this touchscreen and Neuro. Oh my gosh. It is driving me insane. So I just subtracted 1 out of the exponent. So 2 to the 2n plus 2 times 2 to the first.
Could you also do the same thing here, though, and do 2 to the power 2n times 2 to the power 3?
I could. Absolutely. That is a multiplication sign. Yeah, that should be a big dot. That's a big dot. Oh, if you didn't know, you can actually use multiplication as a dot, as a star, or as an X, which I avoid because X looks like a variable. Okay, let's look at number 2. So for number 2, I can rewrite this. Now remember factorial, so I have my n plus 2 times. Now, if I wanted to descend, so n could be anything, right? If I want to multiply it by the next number in the factorial list, what would that be? That would be n plus 1, yeah. So I'm just reducing it by one number. So, well, n plus 2 minus 1 is n plus 1. And then going down again from there, what would it be? It would just be n. And then I put n factorial because I still have to descend, right? Now, if I wanted to go one more, what would I would have n plus 2 times n plus 1 times n times what could be next? N minus 1. Yep. Factorial. Yep. And so forth. All right. So for this next one, once you see one of them, they're all pretty easy. So 3n plus 3. Oh my gosh. So this problem does not happen on my Mac. On my Mac, that is a 2010 model. It works perfectly fine in Neuro. All right, so this one, I can break it to 3n plus 3 times 3n plus 2 times 3n plus 1 factorial. So our negative. What do you mean, Sarah? Yeah. Armin, Antonio. Antonio, what do you mean?
What I was meaning is that, okay, so you said for the n plus 2, it could go to n minus 1, correct?
Good. Yeah.
Okay, so could we also do -1, -2, -3 for the 10? Or does that not work that way?
It does not work that way because so this is a finite factorial. Okay, we don't have a variable involved where n could be anything, right? It only goes down to 1. So if you start at 10, you can't go past 1. You can't go to, well, 0 factorial is still 1, but you can't go -1 factorial. It doesn't work that way. There is a limit.
So if it has a variable, you can, though.
Right, because it could be 100.
All right, perfect. Thank you.
All right, I'm going to skip number 6 because I think it's the exact same as number 3. I don't know why I did that. Whoops. I think I forgot to create one for number 6. All right, any questions on this? It was a super crash course on factorials. Right. All right, so 1.03 test of convergence. This is day 1, by the way. We're going to determine if the convergence of a series. So it's either going to be convergent, divergent, or inconclusive, and we'll get there. All right, we're being recorded. No surprise there. All right, pen, pencil, paper. All right, series convergence. A series is convergent if adding an infinite number of terms in the sequence results in a finite number. So yesterday we talked about a geometric series and how in certain situations, an infinite series, geometric, can give us a finite sum. And in that scenario, what had to be true for us to actually find a solution, a sum of a geometric sequence that's infinite? What must be true? The absolute value of r must be less than 1. Yep. Yep, the absolute value. Nice. Because if the ratio, the common ratio is absolute value is less than 1, that means we multiply it by a number less than 1, absolute value, right? And that number gets smaller and smaller and smaller. It approaches 0. That's why that works. That was from yesterday. All right, a series is divergent if it is not convergent. Fun. Kind of makes sense. If it's not one, it's the other. This is talking about geometric and arithmetic series. Okay, we're going to discuss how to determine this. We have a simple test for arithmetic and geometric, and we also have the ratio test. And the ratio test is probably the most involved. This is where the math gets kind of tricky, and your handwriting has to be good so you can read what you're doing. And again, there's other tests, but we're not going to do those. Okay, some basic ones. So arithmetic series are always divergent. So that's nice to know. This is kind of important, this bullet point. Arithmetic series are always divergent. Can someone on mic tell me, try to explain why that is? Why is that true? Why does that make sense? Volunteer on mic. Want to explain? I'm looking for a simple answer too. Something simple. Did that clear? I can't hear you. Can you guys hear?
She was asking how does adding an infinite number of terms result in a finite number?
Are you asking me because it can't happen? Is that your explanation?
You lost me there.
So I think she was, I don't know, I feel like she's answering the question with the question. So an arithmetic series is always divergent. So let's talk about what the words divergent and convergent means. So divergent, the vocab word to diverge. Simply put, it goes away, right? It travels away from. So a series that is divergent will go to infinity or negative infinity. It doesn't approach any number. That's what divergent is. Convergent means when you add up the sum, or not the sum, but as the numbers get bigger, you're going to approach some number. Most of the time, you'll probably approach 0. You could approach any other number too. That is convergent when your series approaches a specific number. Hopefully that clears up those two words. So an arithmetic sequence is always divergent. Why? Well, simply put, remember, arithmetic, you're either adding or subtracting a number, correct? So if you're going to add or subtract a number, you're either going to go positive infinity or you're going to go negative infinity. Those are the only two choices. Because you're adding the same number every single time. So either going to go up forever or down forever. That's it. That's why arithmetic is always going to be divergent. What you're looking for a simple answer. All right. For geometric, just like yesterday, for a geometric series to be convergent, the absolute value of your common ratio must be less than 1. And that was from yesterday. So looking at these 4 examples, number 1 says, well, 5 plus 5/4 plus 5/16 plus 5/64. First determine, is this arithmetic or geometric? Which one is it? Julia, did you raise your hand? Sorry. Do you have a question, Julia? Can you guys hear me?
I can hear you, yes.
Okay. Julia,
Julia, another question?
do you have a question, Julia? It is geometric. So this one is geometric. So what is the common ratio for this one? What is the common ratio? 1/4. We are multiplying by 1/4 every single time. Great. My 4s look like Y's. The common ratio is 1/4. 5 times 1/4 is 5/4. 5/4 times 1/4 is 5/16, and so forth. Now, let me ask you this. So it's not arithmetic. So it's either geometric is going to be convergent or divergent. Is the absolute value of that number less than 1? It is. So what does that tell us? It is convergent. Let's put C on V. Convergent. So as this series goes on forever, those numbers get smaller and smaller. It starts to approach 0. All right, number 2, arithmetic or geometric? Right, Julia, the asymptote is at 0. It doesn't actually get to 0. It gets infinitely close to 0. So think about this. 5 divided by 1,000,000. That is pretty close to 0. It's not quite 0, but it's pretty close. And then 5 divided by 2,000,000. You're even closer to 0, but not quite there yet. So it approaches 0, but doesn't actually get there. So number 2 is geometric. And what is the common ratio for number 2? -4/3. That looks correct. -4/3. Gosh. I hate Windows. -4/3. -3 times -4/3 is +4. +4 times -4/3 is -16/3, and so forth. So the absolute value of -4/3, is that less than 1? No, it is not. It is approximately 1.33 forever, I think. So that is not less than 1. So that tells us it's what? Divergent. Yep, divergent. Well, guys, after this page, I typed everything else. So we don't have to deal with this much longer on this lesson, at least.
We had a question in the chat asking if you could explain why it's -4/3.
Yeah. So 4 divided by the previous is -4/3. -16 over 3 divided by 4 is also -4/3. That looks like I am writing hieroglyphics or something. Yeah, we just did what we've been doing the last few days. You calculate your common ratio by doing wherever you are divided by the first. We can do that a couple times just to make sure it equals the same thing. Are we good? No worries. I have those all the time. All right, number 3. What is that? Geometric or arithmetic? Yeah, Emily, what's going on? And guys, if you want to feel free to interrupt me on mic, I don't mind. As long as it's obviously a question and not you just talking about random stuff. Are we ever going to use this? Like, when will this ever be useful? I'm so confused. Like in life? Oh, Emily, you're taking pre-calculus. If you wanted math to be relevant to life, you should have taken personal finance, consumer math, or something else. I really don't have a good answer for you. Pre-calc, this leads to there's a lot of stuff that math is used for. Higher level stuff like matrices are used for a lot of stuff. This stuff, convergent, divergent. Honestly, I couldn't tell you. Yeah, you just learn it to flex your math brain. Yeah, you use this to go to a university right out of high school. There you go. It does develop critical thinking skills too. Yep, and that used to be my number one answer. 80. Number three, what is that? Geometric or arithmetic? That is geometric. Yep. And what is the common ratio? Three-fifths? Looks like it is three-fifths. Yeah, we multiply by 3/5 every single time. Three-fifths. Yep. -1 times three-fifths is -3/5. -3/5 times three-fifths is -9/25, and so forth. So that works. Is the absolute value of three-fifths less than 1? It is. So a lot of you have already said in chat, it is convergent. Convergent. And number 4, is it geometric or arithmetic? If it's arithmetic, what is the common ratio? Oh, sorry, common ratio. The common difference. This one is geometric. -3/2. So, yep. Yes, we are multiplying by -3/2 every single time. So 4/3 times -3/2 gives us -2. -2 times -3/2 gives us +3, and so forth. So next question, is the absolute value of 3/2, -3/2, less than 1? It is not. So what is this? This one is divergent. Yep. Yep. -3/2 is absolute value of that is 1.5. That is definitely not less than 1. All right. I obviously didn't have any examples of arithmetic. Well, because arithmetic is always divergent. So on your quiz, on your test, if your sequence, your series is arithmetic and it's asked you, is it divergent, convergent, or neither, or inconclusive, it's divergent for arithmetic. Arithmetic are series where you are adding or subtracting by the same number called the common difference. So you're like, for example, you're subtracting 2 every single time. That would be arithmetic. That was also day 1 of 1.02. Make sure you guys, along with these live sessions or recorded sessions, that you are going through those modules and doing those examples. It's good practice. Okay, now the fun stuff. And luckily, I typed everything after this point, so I don't have to be stressed out or struggle with the writing on the screen. Okay, this page is important. Now, at the very end, you can download these slides, but you do want to write these 3 down. This is the ratio test. We're going to use this when our series is not arithmetic or geometric. This is when we're going to use this test. So just like the bullet point says, since not all series are arithmetic or geometric, we need another way. So we're going to do limits. We're going to do a limit test. So the limit is the absolute value of your series, a sub n plus 1 divided by a sub n. If it's less than 1, then that tells us the series is convergent. If it is greater than 1, it tells us it is divergent. If it equals 1, then it is inconclusive. We don't know what it does based on this test. All right, make sure you guys have a lot of room to write on your paper. These problems are kind of lengthy. Oh boy is right. Oh boy. Not that long. Yeah, not like row echelon. Not that long. Right. All right, so I have these 3 examples. You want to test these if the series is convergent or divergent or inconclusive. So instead of giving you the actual, like some of the numbers of series and have you figure them out like we did yesterday, I'm giving you the formula. I'm at least doing that for you, right? And if a series, and in this case, this is a summation, right? Here's the expression. If you have exponents or factorials, immediately we know it's not geometric or arithmetic. All right, let's do the first one. So if you notice, all those blue boxes, that's all the work. So the first thing we need to do is, well, your a sub n is just the original expression. So that's going to be 2 to the n over n factorial. So there is your a sub n. Now remember the formula is a sub n minus 1, sorry, n plus 1 divided by a sub n. So a sub n is this, so I can go ahead and just write that into the setup. Now we need to find a sub n plus 1. So all we're doing is we are plugging in n plus 1 into all of your n's in the expression here. So this becomes 2 to the n plus 1 divided by the quantity n plus 1 factorial. Why is this box there? Not too bad so far. So there's the top portion, the numerator. Hey, nothing to crying about yet. We haven't done anything. All we did was we replaced n with n plus 1. That's all we did. So wherever you see n in the original problem, there's an n here, and there's an n here. You just replace n with n plus 1, replace n with n plus 1. That's all we did in this step. All right, are we good now? We take a breath. Because that's what it says. So on the previous page, sorry, the previous 2 pages, the formula, this is the ratio test. This is the test. We have to plug in n plus 1 into your n. If I wanted to just replace n with 1, it would say a sub 1 and not a sub n plus 1. All right, good, good. Well, that would be true if n already equaled 1. We don't know what n equals. N could be anything. Okay, so these, if I didn't, so the directions say test the following series for convergence. So I give you a summation problem. So the sum, all this is saying is you have this expression and you're going to sum from when n equals 1 up to infinity forever. That's what you would do if the directions didn't say we're testing for convergence. We're not trying to find the sum, we're trying to determine the convergence of being true, being convergent or non-convergent or inconclusive. So you have to make sure you read the directions. So we want to know in this summation, right? In this summation, now kind of going back to these, yeah, because it says dot, dot, dot. I give you the first 4 terms in this series. I didn't give you that sigma notation to have you calculate those to determine. So I give you the series. I ask you, is it convergent, divergent based on, well, this test here of being arithmetic or geometric? So I could have given you the sigma notation and asked you the same exact question where you have to determine if it's arithmetic or geometric. But that would be too many steps. So, and here, if I gave you the first few terms, deriving that equation would be a pain. So that's why you have these problems in this format. Hopefully that makes sense. All right, so are we all good? We're on the same page now? All right, don't overthink this one. We haven't done anything yet. Okay, so there's a sub n and there's a sub n plus 1. All right, so this goes on the top, the numerator. And there we go. Yeah, we have 15 slides. We're on number 9. We have a lot. And this is the easier of the problems. You know, and we haven't even done any math yet, guys. We haven't done anything yet. We just set it up. Nothing to this point should be difficult. But yeah, it's plug and chug. No, but with a twist, because the chugging can be kind of painful. All right, so we're good to this point, right? We can go on to the actual math part. All right, here we go. All right, so a fraction divided by a fraction, we flip and multiply. We learned that probably, you guys learned that in like first grade? Fraction divided by a fraction, how you take the one on the bottom and you flip it and multiply it. First, second grade, something like that. You know, it was way back when. So that's all we did in this step. So again, we didn't do anything crazy yet. We flipped and multiplied. So now here's the thing. This is where it gets tricky. This is where you have to know exponent rules. You have to know the factorial stuff we did in bell work, because we need to cancel stuff out. So let's look at, see how we have 2 to the n here. We have 2 to the n plus 1. We need to make this, at least one of the factors, look like this. So how can I rewrite this? Remember, we did this in bell work. So how can I rewrite this piece right here? Two to the n times 2 to the first. Perfect. So I rewrote that numerator on that first factor. I broke it down to 2 to the n times 2 to the first using our exponent rules that we reviewed during bell work. We good so far? Okay. Next part of this in terms of factoring, we have an n factorial on the numerator, and we have n plus 1 factorial in the denominator on this factor. I want to break this apart somehow so at least one of the factors looks like this. How can I rewrite this? We did in bell work. N plus 1 times n factorial, correct. We expanded it. We did it in bell work. So n plus 1 times n factorial. Remember, in factorials, we're just decreasing by 1. So we have n plus 1 as one factor, and then decrease it by 1. So n plus 1 minus 1 is just n in factorial. Again, that was from bell work. So easy example, 10 factorial is 10 times 9 factorial. If I didn't have the 9 factorial, it'd just be 10 times 9, which is 90. But 10 factorial is some really big number because it's 10 times 9 times 8 times 7 times 6, and so forth. It does stop at 1. Yep, but we don't know what n is. So remember, so I'm glad, Michael, I'm glad you brought that up because, look, we're doing the limit as n approaches infinity. So if n approaches infinity and I decrease by 1 every single time, will I ever get to 0? Interesting. Oh, yeah, we won't. Because we're doing the limit as n goes to infinity. So I could literally expand that factorial forever. I could say this piece right here could be n plus 1 times n minus 1 times n minus 2 times n minus 3 times n minus 4 factorial. Or I keep going. Unless we do know what n is. N is infinity. infinity. Look, we're doing the limit as n approaches infinity. We kind of know what it is, but really we don't because we can't actually get to infinity. I know. All right. So from this, so are we good on the expansion part of the numerator and denominator? And if you're really struggling with expanding using exponent rules and expanding during factorials, I will find you really good YouTube videos of going through that concept, which I might actually email everyone a couple of videos to watch. Because this is probably this part right here is probably the hardest part for people to wrap their head around because we didn't do it a whole lot. Like from kindergarten up to now, we didn't do it a lot. So it's in a way, it's almost like a new concept all by itself. You've never seen them before? Ooh, you should have learned them. I know when I taught freshmen, I taught it to them. All right, let's go on. So from here, I can now cancel stuff out, which is what we wanted. So remember, we can cancel factors out. So 2 to the n cancels out, 2 to the n cancels out. N factorial, n factorial. This is looking nice. We are left with 2 to the first on top and n plus 1 on the bottom. Oh yeah, that's remember when you cancel stuff up, top and bottom of a fraction, it's just 1 over 1. You don't have to write it. I did. And then that just becomes that. Now, so this goes back to yesterday. We have no variables on top. We have a variable on the bottom. So that means for our variables, it's bigger on the bottom, right? So what does the limit approach? This is from yesterday. It's bottom heavy. What does it approach? It approaches 0. That was the rule from yesterday. So remember, so if the exponents are the same, you take the ratio of the two. If the exponent is bigger on top, there is no limit, right? It goes to infinity. And if the exponent is bigger on the bottom, it approaches 0. That was from yesterday. Make sure you review that stuff. So this limit approaches 0. All right, so we now know the limit approaches 0. So based on the ratio the ratio rule test, the ratio test, divergent, convergent, or inconclusive? Convergent. Yes, all that work just to get to convergent. Now, if you are somebody who goes through these lessons, the modules before class, which is, I highly recommend doing that, you will notice that I am teaching this very different than the way that they teach it in those modules. Wait, so if you check your notes that you should have taken on this page, since the limit, it is less than 1, which 0 is less than 1, it is convergent. If it's greater than 1, it diverges. If it equals 1, it is inconclusive. This is what, once you get down to that, what the limit equals, this is what you compare it to. Okay. Katie, you smart. I make mini proofs. That's actually what I do too. When I actually was learning math. We got 6 minutes left, Antonio. Don't steal my 6 minutes. What's the next problem? Hey, let's try to go a little faster this time. So a to the n is just that stuff. A to the n plus 1, well, you just plug in n plus 1. Give you a moment to catch up. So a sub n plus 1, you're plugging in n plus 1 into the n variables. And then don't forget to simplify. Distribute this 2 times n, 2 times 1. Distribute the 5 times n, 5 times 1. So the numerator becomes 2n plus 2, quantity factorial, and the bottom becomes 5n plus 6. Then we plug it in. The top divided by the bottom. We just use the ratio test formula. Put that stuff in. Flip and multiply. And then from this point, this is where it can get tricky. This is the part where people have trouble because exponent rules and factorial rules, which you need to review. You need to practice this stuff. And we can't. Well, okay, Antonio, what are you thinking we can cross out?
The 5n.
Can we do that?
I'm assuming not because you didn't do it.
Exactly, I didn't do it. Is 5n a factor or a term?
I was meaning in the top part where they were both over each other. I was meaning right here.
Okay. Is 5n a factor or a term?
It's a term because it's part of the equation.
Okay. It is a term, yeah, because terms are separated by plus and minus signs. In a fraction, can you cancel out a term and a term?
No.
Is that allowed? That is not allowed. Only factors and factors can cross out. And this is 5n plus 1. The factor is 5n plus 1. This is the entire factor. If it helps putting parentheses around it, do it, because this is the entire factor. In order to cross 5n plus 1 out, I must have a 5n plus 1 on bottom, and I don't.
All right, that makes more sense. Thank you.
Yep. That's a common mistake. All right. So looking at this, I want to make this 2n plus 2 factorial look like this for one of the factors. So how can I expand this factorial? Read in chat. We did it on Bellworks. So Caitlin, looks like you got it. 2n plus 2 times 2n plus 1 times 2n. You forgot your exclamation point. Yes. They do. You guys, I can sense the pain going on in chat right now because of expanding factorials. All right, guys, I'll find you a good YouTube video on this concept and send out to you guys. But yeah, this really shouldn't be, once you do a couple, expanding this factorial to like what this is should be hard. You're just subtracting 1 every single time. So you got this factor times the factor minus 1 times the factor minus 1 factorial. And I could keep going. I could do 2n minus 1 next factorial, but I don't need to because I want the factor to look like this. which I now have matching factors. So kind of jumping ahead a little bit, I can now cross this factor out and this factor out. And that was the goal, to get rid of the factorial. The denominator. So the 5n plus 6. Can I factor that even more? The answer is no. So it's just 5n plus 6. Can I cross out 5n plus 6, 5n plus 1, anything? Can I cross anything out from these two? No, I can't, because they're terms. The factor is 5n plus 1. The factor is 5n plus 6. I don't have matching factors, numerator, denominator, so I can't do anything with them. Sad, but true. All right, so the numerator, I am down to that. Put it all together is this. Where's my delete button? I do not expect you to multiply this out. But all of you should, put all your math stuff we learned together, from last term, this unit. What is the power of n going to be if I multiplied that out? A power of 3, yes. So that is a third degree polynomial in the numerator. We have 3 factors, that makes sense. So that is n to the third power. And then on the bottom, the denominator, what is the power of that n? N to the first. So I have n cubed on top, n to the first on bottom. It is bigger in the numerator. So from yesterday, it is top heavy. What does that tell us? Is there a limit? From yesterday, there is no limit. So no limit, which means it goes to infinity. And that's why I stressed yesterday, even though yesterday for these problems we put none for the limit, it makes sense. If there's no limit, it goes to infinity. But today, rather than putting none, you put infinity because that's really what it goes to. The absolute value goes to infinity. Okay, so ratio test, those 3 little rules. Is it greater than 1, less than 1, or equal to 1? It is greater. So a lot of you put, because it's greater than 1, it is divergent. And again, I teach this very different than the modules do. The modules are actually kind of hard to understand. So I chose not to do it the way they did. I think my way is a much simpler approach, a much more mathematical for the most part, and works every single time. Wait, how's that infinity? So Emily, that is from yesterday. It's top heavy, so review the notes from yesterday. This is n, let me get my pointer out. This is n cubed in the numerator. And this is n to the first in the denominator. Because it's top heavy, from the rules we learned yesterday, because it's top heavy, that tells us there is no limit. It goes to infinity. Yep, Danica, you are correct. Top heavy, infinity, bottom heavy, 0. Yep. How'd you get 2n plus 2 factorial? Let's see, how did I get that? I went right here.
Just talking about this part right here.
Oh, I distributed 2 times n, 2 times 1. It goes 2n plus 2. Good. All right, guys, it is 11 o'clock. If you have to go, please do. We have another example, which is my last example, but I am also doing 3 examples from your module, your Learn module. And the reason why I'm going through the 3 from the Learn module is because they did a bad job explaining it. So I'm going to go through those 3 exact problems. All right, let's go on to the next problem here. Okay, so we want to test this sequence, the series. So a sub n is just what's given. A sub n plus 1, we just plug in n plus 1 into n. So this one's a little confusing because the original problem already has n plus 1, so it's deceiving when you look at it. All you got to do is wherever you see n, you replace it with n plus 1. Don't overthink this part. Do not overthink it. And we need to simplify. So in the numerator, n plus 1 plus 1, what does this become in the numerator? N plus 2, yeah. And then in the denominator, you have to distribute the 6 times n, 6 times 1, and then add 7 to it. So I did that all in one step. All of you could easily do that in your head. So that's how a sub n plus 1 is equal to that. Nothing difficult yet. And then we go to the setup. We just rewrite those 2 things, those 2 fractions. We flip and multiply. All right, so everything up to this point should be very simple. If you look at it, half the problem is over. It's just the second half of the problem is what makes it hard. All right. So looking at this and this, we want these to match somehow. So this is already -1 to the n plus 1. This is to the n plus 2. So I want this exponent to match this exponent. So how can I expand, using our exponent rules, this numerator? -1 in parentheses raised to the Antonio, you were almost right. Exponent rules. How can I reduce this by 1 to make it match this? Well, I just subtract 1, so we're going to have -1 to the first power, and this becomes n plus 1 for that first factor in the numerator. Remember, same base as you add exponents. Isn't n plus 1 plus 1 n plus 2? Easy way to check it. So all we're doing is we're subtracting 1 out of the exponent to expand it. So this is exponent rules. Using our exponent rules that we've seen in the past, just not a whole lot. All right, are we good on this expansion of this numerator? All right. Okay, so let's look at what else? Let's look at 6n plus 13, 6n plus 7. Can we factor this anymore to make a match? Yeah, nope. Yeah, we can't factor. Nice job. No, we cannot factor those further. They are already fully factored. So those don't change. I don't have to do anything with this because we made this numerator one of the factors equal to this. Remember, like factors cancel out numerator denominator. So this is where we start crossing stuff off. So we have -1 to the n plus 1 cancels out. -1 to the n plus 1 cancels out. -1 to the first power equals what? -1, yeah. Easy question, right? And we just put it all together. You guys could probably skip. You guys could probably skip this step and go right from this step right to this. I'm just doing it to show for completeness, but you could probably skip this step here. Well, I don't know, maybe. So from this step, you have to distribute the -1. -1 times 6n, -1 times 7. That's how I get -6n minus 7 in the numerator. So maybe it is better you show this step in cases where you have a negative. So again, I distributed the -1 to this binomial. Okay. N to the first, n to the first. So we have, it's even, it's the same powers. So what does that tell us to do to find the limit? This is from yesterday. Yep, the coefficients. Take the coefficients of those variables. So -6 divided by 6. Absolutely. Okay, what is -6 divided by 6? -1. And what's the absolute value of -1? 1. Okay, based on the ratio test, less than 1, greater than 1, and equal to 1, what does that tell us? Inconclusive. So based on this test, we do not know if it is convergent or divergent. We therefore must do a different test, which we are not learning. Yay. We are not going to learn it, not in pre-calc. What is it called? I don't know. Julie, you should look that up and get back to me. I have no idea. There's more tests. I can't think of any top of my head. I have a weakness? I don't know everything, guys. I know a lot of stuff. I don't know everything. All right, page 12 of 15. All right, so these problems I pulled directly from the practice module. Because I look through them too, and I look at their examples, and again, the way that they taught this, the way that I'm teaching it, they're very different. If you like the way the module tries to explain it, go for it. I don't think it makes a whole lot of sense most of the time. But this way, so I have this example, and I want to know what the value, so I want to know what the value of R, the limit used in the ratio test. So, yeah. What is the value of R, which is the limit used in the ratio test? So on your practice module, they use the variable R as the ratio test value, but we've been using R as the common ratio for geometric series. So I don't like that they did that. So just know that when they talk about R in this case, they're just saying, what does the ratio test equal? What we've been doing. We got R equals 1 here. We got R equals infinity. We got R equals 0 for those examples. So that's what the module is saying. So that was a little bit confusing. But here's my 3 examples. So let's take a look. All right, let's quickly go through these. Sub n, we plug in n plus 1 to all the n variables, and we simplify. We plug it in, flip and multiply. And then this is where we have to actually do some thinking. Anything. These are the last three. Will it do stuff like that on the quiz? It will do stuff like that on the quiz. For that wording, it will. And again, guys, on your quiz, on your quizzes, on your test, if you are unsure of the way they're asking a question, please message me and I can rephrase it for you if it's presented in a way that you're not used to. But if you go through the learn and practice modules, there should be no surprises. Should be, but occasionally there are. Okay, so 5 to the n plus 1 can, which one can be expanded? Oh, 5 to the n plus 2 can be expanded, yeah. So you can kind of see that we can make this factor, we can expand this using exponent rules to look like this for one of the factors. So somebody already said in chat, we just reduce it by 1. So it becomes 5 to the n plus 1 times 5 to the first. And again, to kind of going the other direction, which is easier, same basis, you add exponents. Is n plus 1 plus 1 n plus 2? The answer is yes. So that means we expanded it correctly. If from this step, if you wrote something weird in this exponent and you asked yourself, is this exponent plus this exponent equal to this? If the answer is no, you didn't expand it right. All right, so let me uncover this one. So just I'm kind of working ahead. I can cross this factor out and this factor out right away, so that's nice. All right. Looking at 2n plus 2 and 2n, can I do anything to cancel more stuff out? The answer is yes. How can I factor 2n plus 2? That's right. That's right, Caitlin. 2 times n plus 1. Now, here's the thing with this problem. If you don't factor and reduce it further, your answer will still be the same. So if for whatever reason you get one of these on your test and you don't factor this to reduce it further, your final answer, you will still come to the same conclusion, which is nice. All right, so I have 2 times n plus 1. So I have two factors. 2 is a factor, n plus 1 is a factor. The bottom, I have 2 is a factor, n is a factor. So what can I cancel out? 2's. Yep. The 2's cancel out because they are factors. Factors and factors cancel out. All right, looks like I am done reducing. So I have n plus 1 on top times 1, and I have 5 times n on bottom. Put it all together. All right. All right, so we have n to the first on top, n to the first on bottom. They're even, so what is the limit of that? What does the r value equal? Remember, we want the r value, the ratio test value. Why is it, why it's not 1, so it is 1/5. So remember, when the exponents are the same, you take the ratio of the coefficients. It is 1 over 5. And the absolute value of 1/5 is still 1/5. So let's say we didn't reduce this part. In the bottom here, you would have 2n plus 2 over 10n. So then you would have 2 divided by 10, which becomes 1/5. You would still get the same answer. That's what I was saying. So using the ratio test, the R value is 1/5. It is less than 1. So what does that tell us? Is convergent. Yep. Convergent. Everyone's happy? Hopefully they're getting a little easier every time we do it. A little easier. I feel like that's like a trend in this class. You guys really cry. You guys are crybabies at the very start, and we do more. There's less crying. It's a little better. Yeah, that's the way it should be, I guess, right? That's okay. This is all new stuff. She use Chrome, not Edge. Antonio, don't all teachers in a way? All right, everyone, let's go to the next one. Okay, this one. So we need to, so I give you this a very simple series, and we need to derive the equation first. So let's do, it's pretty easy, right? Everyone should be able to, I think, see this rather quickly. It's going to be a fraction, of course, right? What's going on? Let's do the easy one first, the denominator. What's going on there? You're just adding 1. So what does the denominator equal to? Remember, this is n equals 1, n equals 2, n equals 3, n equals 4. So formula-wise, what is the bottom going to be? No, we have to derive the equation. So what equation, if we plugged in n equals 1, 2, 3, 4, will give us those terms? So Emily's guessing n plus 1. So if n plus 1, so I'm going to write this down. So let's say my equation is n plus 1 on the bottom, right? And then on the top, we'll worry about that later. So for my first term here, when n equals 1, if I plug in 1 into n, do I get 1? I don't. If I plug in 2, so this is my second term, if I plug in 2 into n, do I get 2? No, I get 3. So what should the denominator be then? All right, Emily, you're being funny now. What's n minus 1 plus 1? Reduce that for me. N. Yes, it is just n. And on the top then, looks like we have 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power. So what is that part of the equation or the expression? To the n power, yeah. 2 to the n power. So this is our equation, and now let's test it. So remember, this is n equals 1, n equals 2, n equals 3, n equals 4, and so forth. Remember, n is the location in your series. So when you plug in 1 into n, 2 to the first over 2, does that equal this? Sure does. If I plug in 2, 2 squared over 2, yep, that's correct. If I plug in a 3 to n, 2 to the third over 3, yep, that's also correct. Let's plug in n equals 4. 2 to the fourth over 4. Hey, that works. So we're just creating the equation that makes that series. Okay, so we now have a sub n is that. So a sub n plus 1 is this. We set it up, flip and multiply. All right, now the fun stuff. What does this numerator become? How can I expand this so I can make it look like this? Two to the n times 2 to the first. Very good. Very good. All right, now we can cancel stuff out. This cancels out. This cancels out. I think that's it. So 2 to the first times n is just 2n. And then we have the n plus 1 on bottom. All right, so n to the first power on top, n to the first power on bottom. What do we do to find the limit? We do 2 divided by 1, which is just 2, and the absolute value of 2 is still 2. So is that greater than, less than, or equal to 1? It is greater. So if it's greater than 1, that tells us it does what? It diverges. Very good. Right, the next one. The last one from your practice module. Looks like 14 of you are still here. Either some of you fell asleep or you really want to see this. I don't know. Some of you really do fall asleep because when everyone leaves and I leave, you're still hanging out in this channel. Dependent, you guys can learn this from the module, right? No. But the examples can be good. So, guys, at least do the examples. I know I say that a lot, but I know a lot of you don't. And yeah, Greek and Latin. Yeah, I learned how to speak Latin. I became a better mathematician. All right, let's quickly go through this last one. All right, there's your a sub n. A sub n plus 1. So the numerator, what does the numerator become? 3 to the n plus 2. That is correct. What does the denominator become? You know, I purposely asked you guys this because I knew nobody would get it right. Everyone's wrong. So this goes back to factorials and properties and operations that you can do on them. So this is 2 times n plus 1 factorial. Even though this is technically a binomial, but it is a factorial, we are mathematically not allowed to distribute a 2 into it. It is not allowed. And kind of like, is Katie still in here? No, she ditched us. So like creating little like mini proofs of doing an example of with numbers and trying to distribute, say, a 2 into it. Mathematically, you can see that it doesn't come out the same. You hate proofs? Sorry. So it just stays the same. Surprise. The good thing, people who are actually here right now and listening won't make the mistake on a test, right? You won't distribute that number if you presented with a problem like this. At least I hope you don't. We learn from our mistakes. No promises. Okay, that's all right. Mistakes happen. Yeah, it is difficult to get 100% on the exams every single time. That is difficult to do. Yep, syntax error, Caitlin. Don't do that. Antonio, you weren't the first one to do that. Yeah, so on your quiz yesterday, which everyone should have done, one of the problems, rather than use n, they used I. And I don't like they did that because I should be reserved for imaginary numbers, complex numbers. I equals radical -1. And they didn't do that. And I think maybe did that because in programming, I is used a lot in loops. Caitlin, I don't know if you use I a lot when creating loops, but it's a common thing to do. Yeah, so you got to see what they do and use the same variable. Kind of a pain. All right, so we just do the setup, multiply, and then we just do the maths. I think by now this should be pretty simple to do. What does 3n plus 2 become? Three to the n plus 1 times 3 to the first, Emily. Oof. And again, we just do a check. These are the same bases, multiplying them together. So same bases, you add exponents. N plus 1 is n plus 2. We did a good job. And then the other ones we just rewrite. They can't do anything else. Oops, sorry, you can. I shouldn't have. Okay, pretend this is still covered. All right, so we want this n plus 1 factorial to be equal to n factorial. So we just have to reduce it by 1. So it becomes n plus 1 times n factorial, because n plus 1 minus 1 is just n. So that's how I went from n plus 1 factorial to n plus 1 times n factorial. We reduced it by 1. There's more. Yep. Right. So let's cancel stuff out here. We got 3n plus 1, 3n plus 1. We got 2 and 2, n factorial, and n factorial. All right, we have no variables on top, and we have n to the first on bottom. So that's bottom heavy. So what does that limit approach? Is our ratio test value equal to? It equals to 0. Very good. And because it is less than 1, that tells us what? It is convergent, yes. Oh boy, and we are done. Well, guys, as always, I hope you learned something. I learned patience today, and I hope you learned some maths.
Will it be okay if I grab a few slides real quick?
Let me stop the recording.
All right, perfect. Thank you.
Only an hour and